Hi, everyone. In this video, we're going to be talking about symmetry and specifically testing for different types of symmetry. Okay, so in our typical two-dimensional plane, we have three different types of symmetry that we can have, or at least at this level, that's how we're going to think of it. Okay, there's three different types of symmetry you can have. You can have symmetry across the x-axis. You can have symmetry across the y-axis, or you can have something called symmetry across the origin. Okay. Hopefully, we're all pretty familiar with x and y axis. So if we have symmetry across the x axis, we have some graph. Okay, we want something with symmetry across the x axis. It might look a little bit like this. Okay, so some equation, not function, but some equation. Okay, obviously there's symmetry across the x axis. If you go on the positive side, if you go on this side, it'll be like a mirror image of what's on each side of the axis. Okay, across the y-axis, okay, maybe you have something that looks a little bit like this. Okay, so this you can flip across in this direction as opposed to this direction. There's another type called across the origin, and we're going to talk about each of these today. Okay, flipping across the origin looks a little bit like this. Okay, there's lots of different examples here, but the idea is you flip it across the y-axis and then across the x-axis as well. Okay, so we go from here to here and then to here, and you get some kind of origin across the y and x-axis at the same time. Okay, so it's a little harder to visualize. With the origin, I think it's easier to do some of the techniques we're about to use in this video. But let's go over a few rules. So again, I wrote these out just like in the last video because there's a lot of writing here, and I don't want to take up all of your time. I'd rather get right to the examples. So the first rule is an equation is symmetric with respect to the x-axis if for every single point x, y, so that's any point that's on the graph, on its graph, then we have the point x negative y is also on its graph. Okay, so if we want to check to see if this works given some equation, all we have to do is replace y with a negative y, and then solve for y, and see, or see if we can get it back into the original form that the equation was given. I guess is a better way I should phrase it. If we can get it back and it looks identical to the original equation, then we know that it is symmetric across the y-axis. Okay, an equation is across the x-axis. I'm sorry. An equation is symmetric with respect to the y-axis if for every point x, y on its graph, negative x, y is also on its graph. So very similar here. To check for this, we replace x with negative x, and we see if we can get it back into the form it was originally in. Okay, if we can, then we know that it is symmetric with respect to the y-axis. If we can't, then it's not. And then lastly, we have an equation that's symmetric with respect to the origin if for each point x, y on its graph, negative x, negative y is also on its graph. Okay, and again, just like in the previous situations, for the previous two, we're going to check with x with negative x and y with negative y and see if that works. Okay, so let's go ahead and take a look at a few examples here. So here we're given 27x to the fourth plus 3y to the fourth equals 17. All right, so for this one, let's see if it is symmetric. I'm not going to graph this. I'm not going to graph any of these, but we're just going to check algebraically to see if there is symmetry. You don't actually have to graph it to see if there's symmetry. We can prove it definitively using these methods. Okay, so let's check with respect to the x-axis. So remember, let's go back up here. If we want to check for symmetry with respect to the x-axis, we replace y with a negative y and see if we can find equality. So we'll have 27x to the fourth plus 3 times negative y to the fourth is equal to 17. Now, hopefully we can see that negative y to the fourth, because it's raised to an even power, is just y to the fourth. So we have 27x to the fourth plus 3y to the fourth is equal to 17. And that is the same. So that means we're good. It is symmetric with respect to the y-axis. Okay, similar for y here. If we're going to check with respect to the y-axis, we'll replace x with negative x, 27 times negative x to the fourth, plus 3y to the fourth is 17. And that'll give us 27x to the fourth plus 3y to the fourth is equal to 17. Okay? And again, we know that because negative x to the fourth is raised to an even power. Therefore, that negative is going to go away. And we have our original equation back. So it is symmetric with respect to both the x and the y-axis. And therefore, because of that, it is also symmetric with respect to the origin. Okay, let's check this one. Here we have y equals x minus 10. So let's check for symmetry with respect to the x-axis. So if we replace y, so to do this, we replace y with negative y. So we'll get negative y is equal to x minus 10. Okay, so we can divide both sides by negative 1. And doing this gives us y equals negative x plus 10, which is not the same thing as our initial equation. So it is not symmetric with respect to the x-axis. Let's try for the y-axis. So we can have y equals negative x minus 10, which we can already see that is not the same thing. So we know that this is not symmetric with respect to the y-axis. And therefore, it's not going to be symmetric with respect to the origin. So, none of the above. All right, now let's take a look at this next one. We have x squared minus y minus 1 equals 0. All right, so let's check with respect to the x-axis. So that means we replace y with negative y. So I have x squared minus negative y minus 1 equals 0. Let's simplify and see if it works. So here we have x squared minus a negative y. That's plus y minus 1 equals 0. All right, so there's no way we can manipulate this to get back our original equation. Therefore, it is not symmetric with respect to the x-axis. Okay, let's check y. So we'll replace x with negative x. So we have negative x squared minus y minus 1. Negative x squared is, because we're raising it to an even power, we're going to have just x squared. So this is going to become x squared minus y minus 1, which is our original equation. And therefore, this works. So it is symmetric with respect to the y-axis. All right, and because we know that it is also not, because we can't replace x with negative x, y with negative y, we know it is not symmetric. It's not symmetric with respect to the origin. So it is symmetric with respect to the y-axis. Okay? Now, last one here, let's check x equals y to the fourth minus y squared plus 1. So if we check the x-axis, we can replace y with negative y. We'll get, forgot to add x equals here. Okay. If we do this, because we're taking these each to even powers, we just get back our original equation. Okay, so nothing changes, and we are good to go there. So we know that it is symmetric with respect to the x-axis. Okay, so now let's check with respect to the y-axis. So if we have negative x is equal to y to the fourth minus y squared plus 1, we can divide both sides by negative 1. Okay, and that'll give us x is equal to negative y to the fourth plus y squared minus 1. So we just flip the signs on everything here. Okay, and that is not the same. Okay, we have negative y to the fourth plus y squared minus 1, not the same. So it is not symmetric with respect to the y-axis. And let's check here now. Let's check the origin. I forgot to mention, it is usually a good idea, unless you can see that it's obvious. It's usually a good idea to check both and see what happens. It's usually good to check for the origin as well. So we can plug in negative x is equal to negative y to the fourth minus negative y squared plus 1. So this will give us negative x is equal to y to the fourth minus y squared plus 1. We already solved this one, so we have x is equal to negative y to the fourth plus y squared minus 1. So this is not symmetric with respect to the origin. Yeah, like I said, it's usually a good idea to go in and double check the origin as well, even if it doesn't pass one of them. That way, at least you're sure and you've confirmed. So yeah, there are here. I guess this video was just here to explain a few algebraic ways to check this. That way, you don't have to worry about graphing it every time, and you can just use one of these tricks to see if it is symmetric with one of the axes.